Okay, you guys, I know that this chapter 15 stuff is really, really tricky, and I just want you to hang in there. We're almost through it. Ask questions, get help, don't panic. You will survive this. We'll work together, get it figured out. This is the last topic of chapter 15. This is called Fischer Projections, and it is quite a bit easier than the stuff that you've already done. So you're really through the worst of it. So hang in there. A Fischer projection is a representation of a molecule. It's a representation of a chiral molecule. And so it is different from our standard method of drawing a chiral molecule because it doesn't use the wedge and the dash notation. Wedge and dash. The Fischer projection is like a shorthand or a fast way of drawing a chiral molecule. It's used a lot in biology and biochemistry. So as we start drawing some Fischer projections, there's a good chance you'll recognize them. And they're going to be really important for us when we get into the later part of this quarter and we start doing biochem. We're going to rely a lot on Fischer projections because it's just a lot faster. It's a faster way of drawing a chiral molecule. So just kind of as a reminder, when we're drawing a chiral molecule, we are using the wedge and the dash notation to communicate the shape of the molecule or the position of the different atoms in the molecule. The molecule that I just drew, remember the bonds that are straight lines, so the hydrogen, the carbon, and the chlorine, these bonds are representing the atoms being flat, as if they were laying flat on the surface of our paper or your table or your desk or whatever. And the wedge bond is used to indicate that that atom is sticking up out of the plane of your paper or your table. And the dash bond is used to indicate that that atom is sticking down into your table or into your paper. Let's try to use mole view to get kind of a visual of what's happening here. If you please log in and play with this because it's a lot of fun. If you're wondering, this default molecule that it starts with, that's caffeine. That's what it always sets us up with in the beginning. So I'm going to draw a pretty simple, just like I did last time, we're going to make just a simple molecule with 4 different things attached to the carbon. So it's going to be chiral. And I'm going to pick some things that have good colors on them to make it easy for us to see in when we turn it into the 3-dimensional shape. So there's my molecule. And remember the hydrogen, the chlorine, and the carbon, they're all flat in this notation, laying flat on the paper. The iodine, purple, is sticking down into the paper, and the bromine is sticking up. And let's turn this into 3D. And so I'm going to rotate this around to get it into that way I just described it. So the hydrogen, which is white, the carbon is the gray sphere in the middle. The green sphere is my chlorine. So I'm rotating it now so that the hydrogen and the chlorine are flat, and we can see that the red sphere, which is the bromine, is sticking up, and the purple sphere, or pink, whatever color that is, the iodine, is sticking down in the back. So this is our standard wedge and dash notation that we use to draw a molecule to represent its chirality or its shape. So let's go back to our notes. Let's start turning this into a Fischer projection. And you know what I want to do? I want to change this drawing that I have here to match what I'm doing in mole view. So what do I need to change? I'm going to turn this into a bromine, and I'm going to turn this into an iodine. So now it matches. Let me double check to make sure. Matches what we're doing. So to convert this into a Fischer projection, we are just going to physically change the way that we look at the molecule. We're going to change our perspective or our view of the molecule. We're going to literally twist it, which I'm going to do in mole view. I'm going to keep the carbon in the middle like normal, but I'm going to move the bromine to the left side and the iodine to the right side. The hydrogen is going to be up and the chlorine is going to be down. And I'm leaving these gaps here because we're going to draw bonds there, but those bonds are going to have direction to them. Like they might be wedges, they might be dashes, they might be straight lines. So we're going to go back to mole view and we're going to look at what this molecule actually looks like when we twist it in this way. So let's just remind ourselves before we switch. We want hydrogen up, chlorine down, bromine left, iodine right. Hydrogen up, chlorine down, bromine left, iodine right. So hydrogen we want up. Hydrogen up, get up there, hydrogen. Hydrogen up, chlorine down. Go. Hydrogen up, chlorine down. Bromine, which is red, I wanted that to the left, iodine to the right. Hydrogen up, chlorine down, bromine left, iodine right. So looking only at the three-dimensional drawing, we're not looking at the 2D drawing up top. Looking at the three-dimensional drawing, here we have the atoms lined up the way we want them. And what we want to analyze now is what's their direction? Are they sticking down? Are they sticking up? And so I've got to kind of rotate this around a little bit to figure it out. But as I kind of angle it, let's focus on just the white and the green, the hydrogen and the chlorine. As I twist it a little bit, can you see the hydrogen and the chlorine are sticking down? They're both angled into the surface of the paper. And as I rotate this a little bit, look at how the red and the purple, the bromine and the iodine, they're both sticking up at me. So the hydrogen and chlorine are sticking down. The bromine and the iodine are sticking up. Hydrogen and chlorine are sticking down. And remember, down is a dash bond. And the bromine and the iodine are sticking up. Those are wedge bonds. So all we've done is just sort of twist the way or change the way we're looking at the molecule, which allows us to draw it differently with wedges and dashes in different spots. This notation right here is the foundation of the Fischer projection. The horizontal bonds are wedge bonds. Horizontal meaning the side to side, and the vertical bonds are dash bonds. Vertical being the up and the down. When we are preparing to draw a molecule in a Fischer projection, we always rotate or look at the molecule from the perspective that its horizontal bonds are wedges and its vertical bonds are dashes. So again, when we're getting ready to draw a molecule in its Fischer projection, we are going to look at it, we're going to twist it around or change our perspective of that molecule until we have it lined up just right that the vertical bonds are sticking up at us and the horizontal bonds are sticking down away from us. Once we get it in this particular perspective or this particular position, we convert it into a Fischer projection. In the Fischer projection, we just use only straight line bonds, put the atoms in their correct spots, up or down or left or right. The carbon, the chiral carbon, is assumed to be at the center. We don't write it with a C. The chiral carbon is in the middle. And the horizontal bonds we know are wedges. And the vertical bonds we know are dashes. Because we all agree that the horizontal bonds are going to be wedges and the vertical bonds are going to be dashes, we don't actually have to draw them. When we look at it, we just say, oh yeah, I know these bonds right here are wedges, because we all use the same notation. And these bonds right here are dashes.